Let's take a look at a lurid USB charger, a little pop-out USB keyring charger, which has a terrible secret, a secret that can destroy expensive electronic equipment. So starting off, this was supposed to be 1500 milliamp hour. I really much doubt it because it's too light to be that, but we'll measure that capacity later on. But it's got a pop-out connector and you can choose the one that it comes with. I chose USB-C, but you can also choose Apple compatible connectors. And when I got it, I plugged it into my USB tester. It's got an input port here. And it didn't light up. And I thought, all right, that just means it needs to be given a charge. And I charged it up a bit and I plugged it back in again. And nothing else happened. So let me plug this lead into the output. You can guess where this is going. And get the meter in. And we'll put the black connection to black and the red connection to red. And the meter says -5 volts. So thankfully, the USB tester apparently has polarity protection. It still works. This thing is putting out the wrong polarity. I think this needs to be explored. How could they do that? That's ridiculous. If this is a standard thing, has this destroyed lots of pieces of expensive electronic equipment? So it looks as though it's clipped together. Let's prise it apart. And we'll take a look inside it, making sure I don't stab through whatever size of lithium cell is in here. I shall zoom down on this. So we've actually got fly leads onto that connector that slides in and out. That's interesting. Let me zoom down. And where it goes onto the circuit board, I wonder if it's the mis-soldered or if the wires are just the wrong polarity. Where is a magnifying glass? The red wires connected to G and the black wires connect to 5 volts. They've mis-soldered the wires on. They've put them in the wrong connections. Wow, that's a bit of a disaster. Now look at the lithium cell. Let's see if we can get this apart. The lithium cell is anonymous. Right, tell you what, I'm going to take the circuit board out of this and we'll at least take a look at this circuit board and analyse it. Now we know kind of what the problem is. One moment, please. Reverse engineering is complete. Let's explore. And I have to say, I'm feeling quite bad for the manufacturer now that somebody in the factory has soldered these on back to front, because other than that, it's a textbook circuit. It's following the data sheet of this chip, the power bank chip, to the letter, and it's also got a dedicated little lithium cell protection circuit on it. So let's take a look at what's on here. Other things worthy of note here. Here is the USB-C charging port, and it has the two 5.1K resistors connected to CC1 and CC2 that signal to whatever device you've got it plugged into that it's looking for current. That's really good. A lot of stuff just misses those off, and that results in things like rechargeable head torches and things like that just don't work if they're plugged into some power banks. In the case of this one, it does send the correct signal back. It has the T-Power TP4333 power bank chip. That's a generic power bank chip. It's got a couple of LEDs pins to indicate the charging and the load status. It uses the inductor capacitors to actually provide the 5 volt supply. And it also has, unused in this case, the switch and the LED arrangement for those power banks with the clicky button and the LED comes on. On the other side of the circuit board are the two LEDs associated with that and the lithium cell protection chip 3160. Not sure what that is. And its little filter network. Everything is textbook. All the correct capacitors are here. The little snubber network here in the input. Let's take a look at the data sheet, which I've just basically augmented. I'm going to tame this down just a little tad. There we go. So the incoming supply comes in here, the USB charge connector. And it has those two resistors going to the 0 volt rail. And it's also got that snubber network that they seem to use, 1.5 ohm and 2.2 microfarad as a filter, presumably to provide stability on the input. And that then goes to charge the lithium cell here, which has its little protection chip and its little network. Now, the resistors are tiny, but I can guess that's 100 ohm and that's 100 nanofarad. That's what they usually have. There's the two LEDs. The bit of circuitry that's not used, the button with the resistor in series for signaling that it wants to turn the LED on or off. It's a sort of double click thing, usually. There's the inductor, the battery connection with its capacitor for stability, and the output of 5 volts with its capacitor for stability that someone just connected onto back to front. That is it. It's actually quite a nice circuit. It's a nice layout in the circuit board. It's all fairly textbook. What a shame that it's just lack of quality control that someone just soldered those connections on back to front. But that is it. It makes me wonder how many are similar. One of the advantages of having the connector just fixed and actually mounted in the circuit board is that, well, you can't really make mistakes like that. It gets soldered onto these standard pads and you can't mix them up. In this case, because they've got the red and the black wire coming out, it means that a tired factory worker or one who's just not been shown how to do things correctly can just tack these on back to front and mess that up. And that's what's happened here. Such a shame. Nice little power bank. Now, the lithium cell that was in it is not a huge capacity. It's currently under test. Once I've got the result of that, you'll find it in the description down below. But I can tell you it's not 1,500 milliamp hour as stated in the eBay listing, because eBay listings lie. But other than that, for a small power bank, it's actually quite neat.